About rational expressions today. Rational expressions are just fractions. That's what rational expressions are. So we're going to do some simplifying and some addition and subtraction, multiplication with rational expressions. And the first thing that we're going to kind of do is find the domain of a rational expression. But we need, in order to find that domain, one of the key things to do in this is finding the domain before you simplify it. You don't need to simplify it and then find the domain. You've got to find that domain before you do your simplifying. As a rule throughout this lesson and then the next one that we're going to, or section that we're going to do tonight, when you talk about domain of functions, you also need to find that domain before you simplify. Okay. All right. So with that being said, let's find the domain and then simplify. That's what we're going to do. Find the domain and simplify. All right, so rational expression. We'll start with a pretty easy one. X minus 7 in parentheses and x minus 1 in parentheses. That's the numerator. The denominator is x minus 1 and x plus 3. Okay. The thing we're playing off of here is the red flags that we talked about in 100 as far as the domain of a function. The red flags that could come up were if you had an x underneath the square root or if we had an x in the denominator. And with rational functions, you're going to have x's in the denominator. So what you want to do to find the domain of that is take that whole denominator and set it equal to 0. So to find that domain, take x minus 1, x plus 3, and set it equal to 0. And since it's already factored, that's factored form that's written there, you just set each factor equal to 0 and solve those. So that'd be, plus 1 there. X equals positive 1. And subtract 3. X equals negative 3. Those are the things x cannot be. So your domain would be all x's such that x does not equal negative 3 or positive 1. That's in set notation. In interval notation, be from negative infinity to negative 3, union from negative 3 to 1, union 1 to infinity. So finding the domain. This is our domain. All that's got to be done before we simplify. The simplifying is the easy part. If you can factor or it's already in factored form, the simplifying is the easy part because you look at the numerator, you look at the denominator, and you find the matching pieces. What pieces match? X minus 1s. They cancel each other out. And our simplified version would be x minus 7 over x plus 3. That's the simplified version. So we're going to find the domain before we simplify, and we simplify by canceling out matching factors. So we're going to be factoring a good bit in today's lessons. All right, so here we have another rational expression. And again, we want to find the domain and then simplify. So we're first going to find the domain by setting the denominator equal to 0. There's a lot of ways to solve that. Square roots is a good method, but you're actually better off factoring because you're going to have to factor it eventually anyway in order to simplify. So I'm going to use factoring. That's a difference of squares because it's x squared minus 25, and 25 is actually 5 squared. So we have a difference of squares there. So that's factoring is x plus 5 and x minus 5. Then I set those equal to 0. Solve. X can't be negative 5. X can't be positive 5. Okay. Now, with that, we write our domain again. Set notation. X does not equal plus or minus 5. That's the short way of writing that. And then the interval notation, we go from negative infinity up to -5, hop over -5, all the way up to +5, hop over +5. That interval notation, not too much fun to write, but it follows that pattern though. Okay. Now here's the great thing. We've already factored the denominator for this rational expression. We know it's x plus 5, x minus 5. The numerator we need to factor because it's a trinomial. We're going to try to factor it with the x method. So 5 and add to be -6. It'll be -5 and -1. X minus 5, x minus 1. Because -5 times -1 is +5, and -5 plus -1 is -6. That's the reason, that's the factors for that. And then when you simplify, you cancel out the matching factors. So the simplified version is x minus 1 over x plus 5. But the domain is always going to be found by setting the original denominator equal to 0. Okay, so if I ask you a question on the Canvas quiz, and I know that there are questions on the Canvas quiz that say just find the domain. It doesn't even say simplify, it just says find the domain. All you've got to do is take the denominator and set it equal to 0 and solve it. So if it asks for just the domain, it's the denominator is the only part you worry about. You set it equal to 0, solve it, and you got your domain. Okay. Let's work on simplifying. That's the part that I think could give us some problems, because factoring is if you're not great at factoring, we got to get better at it. So the only way to get better at that is practice. Okay. So just simplify this. Don't worry about the domain. We're just going to try to simplify this. So anytime you're asked to simplify a rational expression, your job is to factor it as much as possible before you start canceling stuff out. Okay. So I just start with the numerator, look at it, and say, okay, what happens with the numerator? What do we go down through the rules of factoring? The first thing we look for is what? Greatest common factor, which would be what for the numerator? The top. 6 is bigger than 2, so we're going to use 6. And it goes into 30 and 12. What else do they have in common? X. What's that leave in the parentheses? 2x and -5. Yeah. The denominator, does it have a GCF? 4 and 25 don't have anything in common, but there's 2 terms. Is that a difference of squares? So what squared is 4x squared? 2x. What squared is 25? 5. So our factors are 2x plus 5 and 2x minus 5. What cancels? 2x minus 5. So 6x over 2x plus 5. Then we're done. You cannot cancel this x with this x here, because this one is tied together with that plus or a minus. Anytime a term is tied to something else with a plus or minus, you can't cancel part of a expression. You either have to cancel out a complete factor, like we've done here, or they've got to match up perfectly, just exactly the same thing. If one of them has a plus or a minus something, then it's tied together and you can't do that. Okay, so you can't cancel parts of factors. Only whole factors can be canceled out. So we had x squared plus 8x plus 16. Excuse me, that's a minus 8x. It's going to screw that up there. And then on the bottom, let's say negative 2x squared plus 8x. I'll show you a little trick to getting something to work here. We got sign issues. So let's start with the numerator. X squared minus 8x plus 16. So it's got 3 terms. Is there a GCF amongst all 3 terms? No. So I'm going to go to my x method. Multiply to be 16 and add to be negative 8. We'll do that. Negative 4 and negative 4. Good job. Because there's a 1 in front of x squared, or nothing there in front of x squared, I can go straight to my factors as being x minus 4 and x minus 4. Now, here's the key to factoring that denominator, though. You got a negative 2x squared plus 8x. Anytime there's a negative on the front term, when you pull out a GCF, pull the negative out. Okay? So what do those two have in common? They got 2 and x in common. We're going to pull out negative 2 and x. And if I do that, that'll change that to x. And then negative 2 goes into positive 8, negative 4 times. Pulling out that negative on the higher power of x squared there. That on the x squared term really is the trick, I guess, to making sure these work. If you didn't pull that negative out, your factor wouldn't match. You wouldn't have x minus 4 there. You'd have negative x plus 4, which is not exactly the same as any of the factors on the top, which causes a problem. So here, this x minus 4 in the bottom cancels out how many in the top? 1 to 1, 1 cancel, 1. Okay, just gets one of them. So that leaves us x minus 4 over negative 2x. Leave it like that. Okay. All right, let's look at example E. 2x squared plus 7x minus 4 over 5x squared plus 20x. So we're going to factor numerator and denominator. Looking at the numerator, is there a GCF on it? No. What method do I use there? X method. So we want to add to be 7. What's it need to multiply to be? Negative 8. What does that?
8 and negative 1.
8 and negative 1. Good job. Now, I can't go straight to my factors because I've got a 2 in front of x squared. So I've got to do that long step here where I put plus 8x minus 1x in there, and then I group the first 2 together and the last 2 together. What do those first 2 have in common? 2x. That leaves x plus 4 in parentheses. So what do I need to pull out of the second one? A negative 1. That'll leave me x plus 4 in the parentheses. And remember, those parentheses have to match. If they don't match, then things aren't working right. Okay. So my factors on the top are x plus 4 and 2x minus 1. What does the bottom, the denominator, have? Do they have something in common? 5x, yeah. What's that leave in parentheses? X plus 4. Well, that's nice, because now what cancels? X plus 4's cancel each other out. This is 2x minus 1 over 5x. The key is canceling factors after you factor. You got to factor everything first and then start looking for things that match. Okay. Now, the next thing we get into is multiplying fractions or rational expressions. So we're going to start with a number example. Let's take, for example, if I took 6 over 7 times 21 over 30. How do we normally do that in a math class? No, not cross multiply, but I know what you mean. You mean cross, starts with a C. Similar, it's cross canceling. So you're looking at 7 and 21. What does 7 and 21 have in common? 7 goes into both of them. 7 goes into itself once and into 21 3 times. And then what about 6 and 30? What goes into both of those? And that's that common denominator or common factor idea. 6 goes into itself once and into 30 5 times. And then you just multiply straight across. 1 times 3 is 3. 1 times 5 is 5. And you've got that problem done. Yeah, close. Yeah, we'll take it. It's kind of like horseshoes and hand grenades. Get close, you get some points. Now, when you start throwing in some letters, it's basically the same idea. Let's say you had 6x to the 6th over 7 times 28 over 9x to the 4th. Something like that. We're still going to cross cancel anything that we can. So if I look at the 7 and the 28, what do they have in common? 7 goes into both of them. So 7 goes into itself 1 time and into 28 4 times. And then I can look at the other diagonal. 6 and 9 have what in common? 3 goes into both of them. How many times does 3 go into 6? Twice, and into 9 3 times. Okay. Then I look at the variables. Those are factors as well. How many x's are up top? How many in the bottom? Okay, so the 4 in the bottom are going to cancel how many of them in the top? 4 of them. So that will leave how many? 2. So this is going to become x squared, and this is going to go away. Then we just multiply straight across the top. 2 times 4 is 8. X squared. 1 times 3, 3. Let's do 4y squared over 18 times 27 over 8y to the 5th. All right. Same idea. We want to either try to cancel. We haven't had one like this yet where we can cancel vertically, or that we did cancel vertically. Rules for fractions are you can reduce vertically or you can cancel diagonally. Doesn't matter which one you do first. It pays the same no matter which way you do that. Okay. If I look at that first fraction, I see 4 and 18. Both of those are what kind of numbers? Even. So I know I can divide both of them by 2 and reduce that. That'll help me a little bit. So that's going to be 2 and 9. And then, 27 and 8, that won't work over there. I can't simplify that vertically. So then I go to my diagonal. way. 2 and 8, they'll work. 2 goes itself once, into 8 4 times. And then 9 and 27 does the same idea. What about the y's? Where are there more of them? In the bottom right? So there's 5 of them down there, and there are 2 up top. So where's the leftovers going to be? In the denominator, right? So there's 2 up top that cancel how many of the 5 in the bottom? 2. So this is gone. This becomes y to the third. And then we multiply straight across. 1 times 3 is 3. 1 times 4 is 4. Then we have the y cubed still in the denominator. Let me just leave it there. I actually think examples like G and H, I think those kind of problems are harder than the ones that have the big polynomials in them because there's so many pieces that you can cancel. When you get to this problem, this kind of problem, this is where I think it gets a little easier. When you have polynomials, you got maybe x plus 4 and x minus 3 in factored form. And then on the bottom of that, you got an x minus 3. And then you're multiplying by this other rational expression that has maybe x plus 5 up top. And then x plus 4 in the bottom. And x minus 1 in the bottom. To me, this is easier. It looks bigger, it looks tougher, but it's easier. Because now all you're looking for are matching factors vertically or diagonally. Okay? If they're in factored form, that's what you want to look for. So I always look vertically first, just out of habit. There's really no mathematical rule that says you have to do it that way. You can do diagonal first if you want to. It doesn't matter. I just do vertically first because that's the way I've always done it. Okay? If I do vertically, what can cancel? The x minus 3 here cancels the x minus 3 in the bottom. Okay? What else could cancel? Maybe diagonally. The x plus 4 in the top left cancels the x plus 4 in the bottom right. Nothing else can cancel. All that's left is you go straight across and say, okay, there's nothing here. There's an x plus 5. On the bottom, there's nothing. There's an x minus 1. If there were more than one factor, you write it down too. We're going to do more than this one, but trying to get the idea started here. So in factored form, you just cancel out matching factors. So if we had something like 4x squared plus 3x minus 10 over 2x squared plus 3x minus 2 times 2x minus 1 over x plus 4. What we want to do is we want to take this thing and make it look like example I, because example I was pretty easy, right? So we want to make this look like that by factoring everything that we can. Okay? So I'm going to start, just pick a place to start and start factoring. So here we have a trinomial. We look for a GCF amongst that, 4, 3, and 10. Nothing. So then we go to the X method to factor that. So we want something that multiplies to be negative 40 and adds to be 3. This is where kind of some, just a little bit of number sense can help. But you can find this by just knowing multiplication tables. There's things that multiply to be 40. 4 and 10. That's too far apart. They're 6 apart. 20 and 2. That's even further apart. Can't work. 8 and 5. Ooh, 8 and 5 are 3 apart. If we can get the signs right, then we've got the factors. Okay, which one should be negative? The 8 or the 5? Why the 5? 8's bigger and it needs to add to be positive, right? So we're going to use positive 8 and negative 5. So I can't go straight to my factors because I got this 4 in the front, so I've got to do the work where I replace the 3x with plus 8x minus 5x and then do grouping. Those have 4x in common. These have negative 5 in common. So the numerator there in factored form is 4x minus 5, x plus 2. The right-hand one, I'm going to go ahead and tell you, it doesn't factor any further, so we're just going to copy it down. Now, all I got to do is factor this 2x squared plus 3x minus 2. So I'm going to use the x method again on it. This thing needs something that multiplies to be negative 4 and adds to be 3. Smaller numbers got to be easier. What does that? 4 negative 1. Good job. So I've got 2x squared minus 4x minus 1x minus 2. Again, group. It's a plus 4x, not a minus. Mistake. Write it down. So that leaves us 2x and x plus 2. And then in the next place, we pull out a negative 1 and leaves us x plus 2. So the factored form of the denominator is 2x minus 1 and x plus 2. So now this is the problem we're looking at. It's all factored completely. Check vertically. What can cancel vertically? X plus 2 cancels x plus 2. Diagonally. Sound effects help. 4x minus 5 over x plus 4. You're done. A good deal of work that goes into that, but it's still, something you can, it's doable. It's not just incredibly daunting, okay? Now, that's multiplication. The good thing is division works very similar because when you divide fractions, let's say we had 2/3 divided by 15 over 4. How do you do that manually, like non-calculator style? What do you do to the problem? You change it to a multiplication by what? 4 over 15. You flip the second one, and then it's back to multiplication rules. So, okay, well, 4 and 3 don't have anything in common. 2 and 15, so I just multiply across, so that's 8 over 45. Because nothing canceled. Flip the second one, then follow the same rules for multiplication. Okay? Let's do an example of that. So we had 5x squared minus 16. Bless you. X plus 3. Bless you again. Over x squared plus x minus 12. Divided by 30x squared minus 6x over 2x cubed plus 8x squared. All right. So it's a division problem right now. Our job in order to work this is to change it into a multiplication problem. So we flip the second one. Always, yeah, always the second, the one on the right. 30x squared minus 6x. And then the first one stays the same. Factor, 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 factor. I know I can factor the denominator pretty quickly. It'll be x plus 4, x minus 3. And the numerator up here has a GCF of 2x squared. It'll be x plus 4 left. The denominator has a GCF of 6x. That'll leave me 5x minus 1. This one, top left, it doesn't factor quite as easily because it's got the 5 in the front. So I got to do that x method thing. It'd be 15. It had to be negative 16. Yeah, negative 15, negative 1. Good job. So that's 5x squared minus 15x minus 1x plus 3. Group 5x, x minus 3, negative 1, x minus 3. So 5x minus 1 and x minus 3. Once you get it all factored, though, you get to the easy part. The factoring is definitely the hard part. What cancels? X minus 3 cancels an x minus 3. X plus 4 cancels an x plus 4. 5x minus 1 cancels a 5x minus 1. Now we have 2x squared over 6x is the only thing left. Will 2 and 6 reduce any? So, this is really this is all we got left, if that helps to see that. 2 and 6 will reduce. They're both divisible by 2, so that's 1/3. What about x squared over x? Yeah, so there's a x left up here. That big ugly problem we started with, after some factoring and some canceling, turns into 1x over 3. Or just x over 3. Doesn't matter there. I'm not picky about that. All right. So division, turn it into multiplication. Factor. That's what you got to do is factor this stuff. All right. Let's look at addition and subtraction. When you're adding and subtracting fractions, what do you have to have? Common denominators, okay? That's the key to adding and subtracting. So if we take something like 3/5 plus 9 over 20. Okay. What would be the common denominator between a 3/5 and a 9 over 20? What number does 20 and 5 both go into? 5 goes into both of them, but what number do both of them go into? 20, right? 20 goes into itself. 5 goes into 20. So what do I need to do to the 5 to turn it into a 20? Multiply it by 4, right? If I do that to the bottom, got to do that to the top. So that gets me 12 over 20 plus 9 over 20, which would be 21 over 20. All right, let's throw some letters in there. 3 over 10x to the 4th plus 2 over 15x squared. The number part, you do the same way. So what number does 10 and 15 both go into? The smallest one. 30, okay? So we know we got to turn them into 30s. Now, here's what you got to look at with the letters. How many x's does the first one have? 4. How many does the second one have? 2. The least common multiple of that is the largest of them. It's x to the 4th. Okay, so that means the first one doesn't need any more x's. But how many does the second one need? Needs 2 of them. Okay, so we're going to multiply the top one, or the first one, by 3 on top and bottom, and that's it. So that's going to give us 9 over 30 x to the 4th. What do I multiply the second one by? 2 to get the 30. And then how many x's do I multiply by? 2. So that's x squared. Top and bottom. So that's going to give us 4x squared over 30 x to the 4th. Well, the denominator's the same now, so I can combine 4x squared plus 9 over 30 x to the 4th. There's nothing else I can do to that. Doesn't get prettier there. Some of them do. This one doesn't, okay? The key is just getting the denominator the same so that you can write it as one fraction. That's what we're trying to do. So get the denominator the same so we can write it as one fraction. Let's say we had 7 over x minus 5 minus 2 over x minus 5. This one's pretty easy. Why is it easier? I already have the same denominator. So I can just do the subtraction up top. What's 7? Excuse me, what's 7 minus 2? 5. Nothing else you can do. Remember, we can't cancel this 5 with the minus 5 that's in that because it's tied to an x with the subtraction symbol. We can't cancel parts like that. All right. Six over x minus 3 plus 4 over 3 minus x. They do this a little more than I would like for our particular textbook, but it is a fairly common thing for all algebra textbooks to do this. But they give us these denominators that almost are the same, but they're just enough different that you got to do something. Okay. So the key here is looking at that and saying, okay, well, they're opposites on the number and the letter. That the first one has x minus 3 and the second one has a negative x and a positive 3, which is the opposite of the other one. So the trick is to factor out what to change the signs. A negative 1. If I factor out a negative 1, that'll make it x minus 3. Okay. And if that's the case, I no longer I don't have a common denominator. My denominators are different. I've got one denominator that is x minus 3 and another one that is negative 1 times x minus 3. How could I turn the one on the left into the same as the one on the right? Don't overthink it. Yeah, simply multiply it by negative 1. So if I multiply this by negative 1, I got to multiply the top by negative 1. So that's going to give me negative 6, negative 1, x minus 3, plus 4, negative 1, x minus 3. Do that addition in the top. Negative 6 plus 4 is negative 2, negative 1, x minus 3. But then I've got a negative 2 divided by negative 1 times x minus 3. These can simplify, right? Negative divided by negative ends up being positive 2 over x minus 3. Okay. All right. So that's going to lead us into this. 4 over x minus 3, x plus 5, plus 6 over x plus 5, x minus 5. This is where it starts getting to the real algebra part of this. Okay. Least common denominator, LCD, is what I do. And a lot of times I want to find that kind of over here on the side so that I know what I'm going for. Okay. So a least common denominator would include a representative for every factor that exists in there. So these two fractions have factored form denominators. We got an x minus 3, that's one factor. We have an x plus 5, that's a second factor. This one has x plus 5. I've already counted it. That was my second factor, so I don't count them again. And then it has an x minus 5. That's 3 factors. Okay? The way I figure out the least common denominator is I start with the shared piece. What factor is shared between those two? X what? X plus 5 is the factor that's the same. This one and this one. So the least common denominator is going to start with that. Then I just fill in the other stuff. I need an x minus 3 and I need an x minus 5. That makes up my least common denominator. But I always start with a shared piece or shared pieces. Some of them will share more than one piece. Okay? Now, looking at the first fraction, what does it not have? It doesn't have an x minus 5. So I just need to put that in there. If I put it in the bottom and multiply it, I got to do the same thing to the top. What's the second fraction missing? It's got an x plus 5 and it's got an x minus 5, but my least common denominator has an x minus 3 in it. So it's missing the x minus 3. Bottom and top. The denominator does not have to be multiplied out. The bottom part, don't multiply it out. You're wasting your time. The top parts do. 4x minus 20 plus 6x minus 18. On the bottom part, just put your common denominator. And it doesn't really matter what order you put it in there. It's the same. Then simplify the numerator. 4x plus 6x be 10x. Negative 20 and negative 18. Negative 38. X plus 5. X minus 3. X minus 5. And you've simplified. Your common denominator has to have a factor that represents every factor that's already there. Okay. Let's go back up and see that. 7 over x squared plus 4x minus 5 plus 10 over x squared minus 25. What's different about this one and example P? Not in factored form. So let's factor, everybody, in the denominators. Don't worry about factoring numerators. Just worry about factoring denominators on addition and subtraction. Multiplication and division, you got to factor everybody. But addition and subtraction, you only have to factor the denominators, which makes those a little bit better. So first fraction, Multiply to be -5, add to be 4. Negative, or -1 and +5. Is that what you said? All right, so that would be 7 over x minus 1, x plus 5. The second one is a difference of squares. What are the factors? X plus 5, x minus 5. What's the common denominator? What's the shared piece? Start with that. X plus 5 is a shared piece. And then list the other factors. We've used x plus 5, so we have an x minus 5. And we have an x minus 1. What does the first fraction need? This one here. It needs x minus 5. Put that to the top and the bottom. What does the second fraction need? X minus 1. Multiply out the numerators. So that's 7x minus 35 plus 10x minus 10. The denominator is just x plus 5, x minus 5, x minus 1. Simplify the numerator as much as possible. 7 and 10 is 17 minus 45, x plus 5, x minus 5, x minus 1. Common denominators. Factor everything first. They're not going to be crazy hard on the factoring part of addition and subtraction because there's so much extra other work you've got to keep doing. So the factoring shouldn't be just incredibly difficult on those, but still, it's that process that you're going to have to go through. Okay. All right, so that's the first section for tonight. Second section, it's got a lot of stuff in it too. So, but I don't think it's as much. It's still a lot to know. Either way. Oh well. Still got to know it. Section 3.5. Rational functions and their graphs. A rational function, the parent function for that is 1 over x. I'm going to open up my graphing calculator because we're going to use it some in a minute. Okay. So, rational functions typically have a domain. Well, this one would have a domain where x does not equal 0. Or it would be -infinity to 0, union 0 to positive infinity. That would be the domain. The range, if x can't be 0, then y can't be 0 for this particular function. So the range is the same. That's not always the case, but for the parent function, it is. Okay, the parent function means the most basic rational function that we can come up with. Okay, and then there's this thing called a vertical asymptote. Yes, there's a P in there. It's at x equals 0. And then there's a horizontal. At y equals 0. I'm going to show you the graph of this so you can kind of see what's going on there. Okay. Once you get that copied down. Vertical asymptote, that just means there's this imaginary line that the graph approaches but never crosses. Horizontal asymptote's the same idea. although they can cross horizontal asymptotes. They don't do it very often, but it can happen depending on the complexity of the rational function. But in this case, it doesn't cross the y equals 0 line. So the graph in y equals, clear out some stuff I was doing earlier today, 1 divided by x. And what we're seeing here is it's flattening out at y equals 0. That's the horizontal asymptote. It's the x-axis for the parent function. The y-axis, x equals 0, is the vertical asymptote. See how this curve kind of borders up against that, and it can't go through there? That's what an asymptote does. Okay? For the most basic functions, parent function, that it's 0 and 0 for the y and the x asymptotes. We're going to learn some more for the more complex problems, but we're going to start off talking about transformations. Okay, we're going to describe the transformation. So we got to remember some rules for transforming. When you're transforming or translating a function, things that happen on the inside are horizontal. Things that happen on the outside are vertical. Remember that from shifting functions in previous lessons. So let's start with this one, and I think after we go over a few of them, it'll kind of jog your memory on some of this stuff. X minus 2, that's an inside thing because it happened directly to the x. If it happens directly to the x, then it's a horizontal movement. So this is right 2. Okay. That's the transformation of the parent graph. If it were g of x equals 1 over x plus 5, that's an outside thing because it didn't happen directly to the x. So that's going to move it up 5. A minus sign on the inside goes to the right. A plus sign on the inside goes to the left. On the outside, pluses go up, minuses go down, or like they're supposed to. Okay. Example C combines the two. 1 over x plus 3 minus 6. What does the plus 3 do? Left 3. The minus 6, down 6. And that's basically what we're doing here is we're just taking this and we're looking at it and saying, okay, what happened to the original one by looking at the equation? Let's do one more. Say g of x is equal to 4 over x. And this one's a kind of a tough one. Is that 4 directly with the x? That's on top, right? So what that does is it treats it like this. It's 4 times the parent function. So this is a vertical stretch. If that were a small fraction, like 1/3 or 2/5 or something like that, then it'd be a vertical compression on the outside there. If it were with the x in the denominator, if it's a big number, it's a horizontal compression. If it's a small number, like a small fraction, like it was 1 over 0.25x, then that's a horizontal stretch. It goes the opposite. Big numbers on the outside stretch. Big numbers on the inside compress. Okay? It's the opposite on the inside as to what it is on the outside. So remember those rules out of that. All right. Let's look at important parts of rational functions. Okay, this is a lot of vocabulary here, so but very important parts. Important parts of rational functions. The domain, it's going to be found the exact same way we found the domain for the rational expressions in section R5 that we just finished. You set the denominator equal 0. Set denominator equal to 0. Simplify and holes. Not every one of them will simplify, but you always try to do that after you found the domain. Okay? So we're going to factor everything, set the denominator equal to 0. We will then simplify after we found that domain, and we look for what's called a hole in the graph by looking at those canceled factors. Those canceled factors point us to where holes could be in our graph. Okay. The next thing we look for are asymptotes. Okay. Asymptotes. There are 3 kinds of asymptotes. Okay. The first kind are vertical. Vertical asymptotes are a lot of times the same as the domain. Unless something canceled. So like if you had x plus 4 that canceled out, you know, or x plus 4 in the denominator, then x equals -4 is one of your domain restrictions. That's also a vertical asymptote, x equals -4. There's an imaginary dotted line at x equals -4 if that's the case. Okay. Vertical asymptotes come from the denominator of the simplified function. We'll look at examples of this and see what's up, but they come from the denominator of the simplified function. That's where vertical asymptotes come from. The second type of asymptote we could have is a horizontal asymptote. We saw that the basic parent function of 1 over x, you know, y equals 1 over x, that had a horizontal asymptote at y equals 0. Horizontal asymptotes, they only occur if the degree of the numerator is less than the degree of the denominator. Well, that's not the only time they occur, but if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote, we'll abbreviate that HA, horizontal asymptote, is at y equals 0. So if you had x squared over x cubed, that's the degree at the top is 2, the degree at the bottom is 3, top is smaller, so the horizontal asymptote is y equals 0. Okay. A horizontal asymptote also occurs if the degrees are the same. If the degrees are equal horizontal asymptote, HA, is at the ratio of the leading coefficients. So that's like if you had y equals, 7x squared plus 5x over maybe 9x squared minus 2. The degrees are exactly the same because the top one has the highest exponent of 2. The bottom one has the highest exponent of 2 on the variable. So the degrees are both 2. The horizontal asymptote would be at y equals the ratio of the leading coefficients, 7 over 9. That's where your horizontal asymptote would be. That's an example of that, if you had a horizontal asymptote. Okay. Now, the third type of asymptote is what we call an oblique. And you may hear it called slant asymptote. Oblique asymptotes only happen if the degree of the numerator is one more than the degree of the denominator. If that's what's happening, then an oblique asymptote, OA, we'll abbreviate that, can be found using long division. We'll go over doing that again. Okay. Vertical asymptotes can happen on every problem. Oblique and horizontal asymptotes never occur together. Okay. That's important to know. Oblique and horizontal asymptotes never occur together. You can have vertical asymptotes and horizontal asymptotes. You can have vertical asymptotes and oblique asymptotes, but you will never have all three. And you will never have horizontal and oblique at the same time. Okay? It's a rational function. That does not happen. Okay? If the degree of the numerator is more than 1 larger, so the rule for oblique is you got to have like x cubed over x squared, or x to the 5th over x to the 4th. If it's x to the 4th over x squared, that's 2 more, then there's no oblique and no horizontal. You can have vertical asymptotes and not have a horizontal asymptote or an oblique. You don't have to have those. Vertical asymptotes should be there. Horizontal and oblique are only if it meets the conditions for them. You've got to know those conditions. Okay, you got to know those rules. So you need to kind of start chugging that back into the memory there and go from there. All right, so we're going to look at some examples of rational functions and try to find all this stuff for them. We'll just do a bunch, do 1, 2, 3, 4, 5, 6 examples of those. Should get us a lot of different scenarios because there's a lot of them to get with this and kind of catch on to those rules and start applying them. to what we're doing, okay? So we're going to state the domain and find all asymptotes. Okay. This is an E. Yeah, it is. All right, so here's our function. F of x is equal to x plus 1 over 2x squared plus 5x minus 3. Okay. So we're looking at that. We're saying, okay, the first thing they said was state the domain. So I'm going to do that first because I have to find my domain of a rational expression or a rational function before I even simplify it. Okay, so that's why I want to start with that. Even though I could follow some of the rules for the asymptotes here, I'm going to do the domain first because I need to do that before I simplify. So the domain, we're going to take the denominator and set it equal to what? 0. 2x squared plus 5x minus 3 equals 0. I'm going to try to factor that because it's a rational expression. So factoring is going to be the thing you want to do so that you could cancel out something if it will. It's not always going to, but it is, you know, it's what you're after. So factoring is your method for solving. Multiply to be -6, add to be 5. Who does that? 6 times -1 is -6. 6 plus -1 is 5. Good job. 6 to -1. So I'm going to put 2x squared plus 6x minus 1, x minus 3. And group that. 2x, x plus 3, minus 1, x plus 3. So I group 2x squared and 6x together and pull out the GCF of 2x, leaving the x plus 3. These two have a negative in common, so -1 comes out. That's x plus 3. And then my factors become 2x minus 1 and x plus 3. And then I just set those equal to 0. 2x minus 1 equals 0, x plus 3 equals 0, and solve them. So x can't be 1/2, and x can't be -3. Those are the restrictions on my domain. So my domain, x such that x does not equal -3 and 1/2. Interval notation would be from -infinity up to -3, union -3 to 1/2, union 1/2 to infinity. There's my domain. Now here's what I do next. I look at that and say, can I simplify from there? Does anything cancel in that factored form? No. Okay. If nothing cancels, then your vertical asymptotes are at the same values that x cannot be in your domain. So we got two vertical asymptotes with this one. It's at x equals -3 and x equals 1/2. Okay? If nothing cancels, it's exactly the same as your domain. X equals -3, x equals 1/2. Two vertical asymptotes for this one. Now, since nothing's simplified, we can then look at our degrees the same way we did, with the original. Like, there's two factors down here. It's got x and x, so the degree of that's x squared. But it's easier to see here because that's x squared. It really is 2 there. So the degree of the top is 1. The degree of the bottom is 2. So the top is smaller than the bottom. So that means there's what kind of asymptote? Which one? Horizontal. If the top is smaller, it's horizontal. Okay? What is it? Horizontal asymptote at where? Where? What does the rule say? If the degree of the top of the numerator is smaller than the degree of the denominator, the horizontal asymptote will be at y equals 0. No calculation to do, no math to work out. It's just a rule. Okay. Horizontal asymptote, when the degree of the top is smaller than the bottom, it's at y equals 0. If it has a horizontal asymptote, what does that mean about oblique asymptotes? It can't have one. So your oblique asymptote, you'll say it has none. Okay? Vertical asymptotes, horizontal asymptotes, or oblique asymptotes. Reporting on all of those. Let's do another. Here's our function. F of x is equal to 4x minus 2 over x plus 1. This one's nice because you don't have any factoring to do. You got 4x minus 4. You can do a little factoring up top, but the denominator is the main thing that we need to factor. So let's find the domain first. How do we find the domain again? Set what equal to 0? The denominator. So the denominator is x plus 1. So if we set that equal to 0, x cannot be negative 1. So our domain is x, such that x does not equal negative 1. Or from negative infinity to negative 1, union negative 1 to infinity. Bouncing back and forth between set notation and interval notation. Okay. Now, the bottom part didn't factor. The top part could factor a little bit. I could pull out a 2, but that leaves me 2x minus 1 over x plus 1. And that doesn't simplify any. Okay? Nothing simplifies. So that means my vertical asymptote, and I'm going to steadily abbreviate more and more as we go through these problems. Vertical asymptote is where? X equals negative 1. Because nothing's simplified, it's the same thing as I found for my domain. We'll see in a minute what happens when it simplifies a little bit. What's that do to your vertical asymptotes? Okay? Now, rules. What's the degree of the top? What's the degree of the bottom? 1. So that means it has what kind of asymptote? If they're the same, does it have a horizontal or oblique? Go back to your rules. It's horizontal. If the degrees are equal, the horizontal asymptote is at the ratio of the leading coefficients. So let's go back to our problem. What are the leading coefficients in the original problem? 4, and what's in front of this x here? 1. So the horizontal asymptote is at y equals 4. 4 divided by 1. Which means the oblique is what? going to be none. Because remember, you cannot have horizontal asymptotes and oblique asymptotes at the same time. Kind of like you cannot have donuts and a six-pack of abs at the same time. Right? Isn't that the rule? Unless you have incredible genetics or a brutal workout schedule. I have neither, so I'll just have donuts. Okay. Got to die from something. Might as well be Krispy Kremes, I guess. All right. Let's look at this one. F of x, x squared plus x over x minus 1. Again, going to find the domain first. How do we find the domain? Easy thing. Set the denominator equal to 0. X minus 1 equals 0. And solve that. X can't be 1. So domain x such that x does not equal 1. Negative infinity to 1 union 1 to infinity. You're getting pretty good at that. Okay. Now, next thing to do is try to simplify it. So does the numerator factor? It's got a GCF of x. But does anything cancel? No. Almost. We had an x minus 1 and an x plus 1. That was close to the same. It's not exactly the same, so it can't cancel. So nothing cancels. If nothing cancels, what do we know about our vertical asymptotes? It's the same as the domain. So it would be at x equals 1. Horizontal asymptote. Let's look at the degrees. Since nothing cancels, I'm going to go back to the original. What's the degree of the top? It's the degree of the bottom. 1 more than the bottom. 2 is 1 more than 1, right? That means there's what kind? Oblique. So in the horizontal, we'll say it's none. All right, so there's no horizontals, but there's an oblique. The oblique asymptote, it's found by doing long division. Okay? Been a minute since you did long division with polynomials. So let's do one. Okay? We're going to take x plus 1 and divide it into the numerator. So we're actually going to carry out the division that the problem starts with. That's a division problem. It's written like a fraction, but it's a big division problem. We're actually going to carry out that division. So we're dividing x plus 1, or x, excuse me, that's x minus 1, into x squared plus x. If you remember doing this, you look at the part in front. What times x would get me x squared? Just an x, just a plain x would get x squared. X times x would be x squared, so I need an x. So I'll put that there. And then I multiply that out. X times x is x squared. X times negative 1 is negative x. And I'm subtracting that whole thing. So the x squareds cancel. X minus negative x is 2x. Technically, there's a plus 0 there. I brought that down. What times x would get me 2x? 2. So I need a plus 2 up top. Then distribute. It's 2x minus 2 and subtract. Those cancel. That becomes 2. Now we're done because there's nothing that gets 2 from a plain x. You can't get 2 from x. Now, our oblique asymptote is the quotient there. Oblique asymptotes are linear equations. Oblique asymptotes will always have the form y equals mx plus b. So when you do that long division, you really should only have to carry it out 2 steps. Shouldn't have to go any further than 2 steps, because the rule with the degree being 1 more than the bottom, 2 steps is all it should even go. It doesn't matter what the remainder is. The remainder is just, it's there. It doesn't matter. The y equals mx plus b part, the quotient, what's up here, the 2 steps that you did with your long division, that's going to be your oblique asymptote every time, if there is an oblique. Vertical asymptotes, almost there every single time. Horizontal asymptotes, pretty common because they've got a lot more options to get there. A oblique asymptote is a unique thing because it only happens when the degree of the top is 1 more than the bottom. It's very specific about when that's going to happen. So that's what makes the obliques kind of rare. Do another. F of x, 3x squared plus 5x minus 7 over 6x squared minus 150. Fun one. I love that. Two more after this one, guys. Hang on with me just a little longer. All right. What we do first? Domain. How do we find domain again? Set the denominator equal to 0. What method are we going to use to solve that? What do you mean? What's that called? What's the name of that? That's right. What's the name of that?
Difference of squares.
Good. Difference of squares method of factoring. So the first thing I'm going to do, though, before I can do that, is got to get the GCF out. 6 and 150 have 6 in common. I'm going to pull a 6 out. 6 goes into 15 twice with 3 left over, and then the 30, that'd be minus 25. And then, yes, this is the difference of squares. X plus 5, x minus 5. We've seen that one a lot. So we get x plus 5 equals 0, x minus 5 equal to 0. And then our domain is x can't be plus or minus 5. X such that x does not equal plus or minus 5. Interval for that, negative infinity to negative 5, union, negative 5 to 5, union, 5 to infinity. Pretty ugly, but that's okay. Set notation is pretty clean looking, though. All right, so at this step, we've got the factored form of the denominator. That's key to have that. That's why I'm using factoring instead of adding 150 divided by 6 and then taking square roots. Factoring is what I want to use there to solve those. And they're going to give you ones that do factor because of that reason, because of the section you're in, your irrational stuff. They want things to factor. So they'll give you good ones that do factor. So the next thing we want to do is look to see if we can simplify the whole shooting match here and see if it'll cancel out some stuff. So denominator is 6x plus 5, x minus 5. I'm going to try to factor the numerator. So negative 21 and add to be negative 5. Things that multiply to be negative 21. That's limited because 21 is pretty special. It's 7 and 3 or 21 and 1. That's the only factors there are. Do any of those get negative 5 when you put them together? No. So what's that mean about the numerator? It won't factor. It won't do anything. So we end up with this, 3x squared plus 5x minus 7 over that. So it didn't simplify at all. What's that tell us about our vertical asymptotes? X is negative 5, x is positive 5. Those two same things we got in our domain. Now we got to decide horizontal or oblique. So if it didn't simplify, I'm going to go back and look at my original because it's easier to see there if it doesn't simplify. What's our degrees doing? They're the same, which means it'll be what? Where? Three over what? Leading coefficients. If they're the same, it's the ratio of the leading coefficients. The leading coefficients are those two right there, 3 and 6. So 3 divided by 6, which is y equals 1/2. What about the oblique? None. None. All right. 2 more. These are not too bad. They actually work out pretty nice. Let's say we had f of x is equal to 3x squared plus 1 over x minus 2. Pretty easy one here. What do we start with? Domain. Always going to start with that. Okay. This one's pretty easy because all you do is set x minus 2 equal to 0. X can't be 2. I'm just going to build it around that. And negative infinity, 2 union 2 to infinity. There's our domain. Will the numerator factor? No. Well, that's good in a way because that means we know what our vertical asymptotes will be. What will it be? X equals positive 2. Now we got to decide, do we have a horizontal asymptote or do we have an oblique asymptote? Which one again? Why? Yeah. The degree of the top is 1 more than the degree of the bottom. So to find that oblique asymptote, we're going to do long division. So we're taking x minus 2 and dividing it into 3x squared. I'm going to go ahead and put a 0x in the middle plus 1 because that's one of the things you do when you do long division is if there's a missing term, you put it in there. Okay. Now, as I'm working that, I look at this x here and say, what times x gives me 3x squared? 3x. Then I distribute that. So 3x squared minus 6x and subtract. X squareds cancel. That's what we make that happen. And then we have 0x minus negative 6x, which would give us positive 6x. And I'm bringing down the plus 1. And then I look at that and say, okay, well, what times this x would get me 6x? Plus 6. And that's 6x minus 12. Subtract. X is canceled. Really don't even have to carry out that step because we now have a slope-intercept form. Y equals mx plus b. Y equals 3x plus 6. let's graph this one because we haven't graphed one on the calculator yet. I want to let you see all of this stuff on the calculator because it doesn't draw everything, but we can make it draw some of it. So I'm going to graph the original equation. So 3x squared plus 1 is that right? Over x minus 2. So put the 3x squared plus 1 in parentheses divided by parentheses x minus 2. When you graph that, these little loopy things there, the other one is off screen here. Here's what I want to do. I know there's a vertical asymptote here, right? There's a slant asymptote here. That's what it's going to look like. If there's a slant asymptote, it's going to have a kind of a cut like that. If it's a vertical and a horizontal, it's going to look more like that 1 over x that we had, where it's just kind of, you know, doing that. It's hard to do. That I can't do it on, but let's graph that oblique that we did. I'm going to go to y equals, and I'm going to go to y2. I'm going to type in 3x plus 6 because that's the one we found. Look at how that graph goes up there. If I zoomed out here, just so you can see it a little bit better. Look how the two pieces kind of line up to the edge of that oblique asymptote. That's what's happening here. That's what we're finding. We're finding the things that make that graph look that way. So you can graph it with the calculator and get an idea of what you're supposed to be finding. Okay, if you're supposed to be finding a slant asymptote, it's going to look like these blue pieces in some way, shape, or form. They may be turned a different direction, but they're going to have like a slanted piece on them. If it has a horizontal asymptote, it's going to go like that on both sides. If it has a slant, you can tell by the graph which ones it has. So it kind of gives you a clue about what you're supposed to find. Okay, let's do one more, and then we'll get out of here for the evening. I know it's pretty heavy stuff tonight. So f of x, let's do x squared plus 5x plus 6 over x squared minus 4. Excuse me. All right, what we're going to do first? Domain. Set x squared minus 4 equal to 0. And again, there are ways to solve this other than factoring, but factoring is the method you want to try to employ because it's going to help give you a leg up on the next step. Okay? That's a difference of squares. X plus 2, x minus 2. So our domain, you're going to set those equal to 0. Negative 2, positive 2. So domain is x such that x doesn't equal plus or minus 2. That's nice. The next thing I'm going to do is I'm going to check for simplifying. None of them we've done so far simplified. Maybe this one does. I don't know. Let's look at it. The denominator's factory is x plus 2 and x minus 2. What about the numerator? Multiply to be 6 and add to be 5. Multiply to be 6 and add to be 5. 6 times 1 is 6, but 6 plus 1 is 7. About 3 and 2. 3 times 2 is 6. 3 plus 2 is 5. That'd be x plus 3, x plus 2. Woo-hoo. What's happening here? We got factors that cancel, right? You got x plus 2 canceling and x plus 2. What that's going to do is going to create our vertical asymptotes being different than our domain this time. It just takes one of them away. What's the only vertical asymptote that's left? Not -2, because it's the one that got took away. What does x minus 2 equal to 0 give us? +2. It's x equals +2. That's the one that's left. So we only have one vertical asymptote on this one, even though we had two values in our domain. That simplifying step is what did that. All right, so we have a vertical asymptote at x equals 2. Excuse me. What about horizontal and oblique? We got to decide if on what we've got. Horizontal where? So y equals 1/1, right? Y equals 1. We also have a hole at x equals -2 because of that cancellation. That's just a little bonus information for you. Is that you have, anytime you have a factor that cancels out, whatever that factor was equal to 0, there's a hole at that x value. And you could find the y value that goes with it by plugging that in if you needed to. But in your textbook on page 346, there's a nice little summary box of all of this stuff in there. There's a nice summary box there. So if you look in your textbook and that box might be handy, you might snap a picture of it with your phone so that you don't have to flip back and forth to it all the time if you're doing some practice. Might be handy to have for your Canvas quiz. Problems that I would suggest from R5, it's on page 47, 1 through 78, any of those in that set. And in 3.5, page 351, there's a bunch, 1 through 106. You don't have to do everything on all of those. It's going to ask you for specific things on different parts of that. That's a big section because there's a ton of information in it in 3.5. And we covered it pretty quickly tonight. So by all means, I'll have the video